All right, open up your book to section 6-4. We're on page 300 in your book. The title of this section is the Radian Measure for Angles, or the Radian Measure of Angles. The objective is given an angle measured in degrees, convert it to radians and vice versa. And given an angle measured in radians, find the trig function values for those radian measures. All right. Couple of things to note here about radians. First of all, you probably should recognize that on your calculator, when you go under the mode menu, you find that there is an option between radians and degrees. Those are different ways that we can measure angles. But one thing you should realize is that a radian is just another unit of measure for us. Now there is a little bit more that we can do with it, and we'll talk about those things here as this chapter progresses, but if I just remember that it's a unit of measure, that'll help me get started with this. Like, for example, when I'm talking about lengths, lengths can be measured in a number of different units. I could have a length measured in feet or miles. I could have it in metric, centimeters or meters or kilometers. Those are all just units of measure. If I'm measuring area, that could be in square feet or square miles or square kilometers. It could be in acres. A lot of different units I have when I'm working with area. For volume, I've got cubic centimeters or maybe cubic inches or gallons. Those are all different ways that I can measure a volume. For angles, I've got degrees, and now I've got radians. One thing that you've learned that when you're working with different units is that there's a conversion that you need to know in order to go from one set of units to another set of units. And that's really all I need to figure out here between radians and degrees is what's the conversion. If I want to go from feet to inches, I need to know that there are 12 inches in 1 foot, and then I'm all set for doing a conversion. If I want to go from inches to centimeters, I need to know that 1 inch is 2.54 centimeters, and then I can do a conversion. But the other thing you should realize is that at this point, you should be comfortable with all these other units that we have up here. And that if I give you a problem that's measured in one of these units, that you don't go, oh, I got to convert this to a different set of units because I'm not comfortable with working with that set. If I give you a problem that's measured in meters, I wouldn't expect that you would immediately convert it over to feet because you just aren't good working with meters. You go, at this point, I can work with whatever units you give me. Just tell me the numbers and I'll work with it. The same is true here when we work with radians and degrees. I know at first it might feel a little bit awkward working with radians, and maybe at first you might want to convert radian measures over to degrees every time before you start working with that problem. But eventually we want to get over that. Just go, it doesn't matter what units you give me, just give me the units in the problem and I will solve the problem. I shouldn't have to do a conversion from one unit to another and then back in order to answer your question. To give you an example here of a relationship between radians and degrees, if you grab your calculator, let's find out what the sine of 60 degrees is and compare that with the sine of pi over 3. Now, sine of 60 we should know from your 30, 60, 90 triangle. If we sketch an angle of 60 degrees in our first quadrant, and then if it helps you, sketch your reference angle there and your reference triangle. So this would be root 3 and 1 and 2. More importantly, what's our value? U, V, and R is what we're coming up with. So U is 1 and V is root 3 and R is the 2 that I've got sketched there. So before I even calculate this, I should know that the sine of 60 degrees, of course, is equal to V over R, which would be equal to root 3 over 2. All right, but let's grab our calculator and see if we in fact get that. And let's compare that with, I guess it wants to find the sine of pi over 3. And that's going to be measured in radians. All right, so first thing let's make sure that we're in degree mode because that's how we're going to do this first calculation. So Make sure you're in degree mode. And then if I take the sine of 60 degrees, I get 0.866. That might not be a number you recognize, but if I compare that with what we said there, that was root 3, or should be root 3 divided by 2. Yeah, in fact, that's the value we get. Okay. Now let's compare that with the sine of pi over 3. If we go to our mode and we switch over to radian mode, and now take the sine of pi over 3. They want me to compare it with sine of pi over 3. And oh, check that out. We get the exact same thing. Looks like perhaps 60 degrees and pi over 3 radians must somehow be related there. Let's grab a picture of that. And let's write that down. So ended up with root 3 over 2, which is the 0.866. And when I found the sine of pi over 3, that was also 0.866. Oops, let's put a 0 in there. One thing you'll note here in this problem, too, is that it's going to be critical that we indicate that when we're working in degrees, we put a degree mark up there, so that's 60 degrees. I know that's in degrees. With the radian, there's no mark we put in there, so if there's no degree mark, we automatically assume that it's going to be radians we're dealing with. When I see the pi over 3 or anything else there that doesn't have a radian mark, or sorry, doesn't have a degree mark, I know it's going to be radians there. All right, so let's talk about how radians are actually defined. And to define them, they give you a nice little picture of this in the book there. But if you start with a unit circle and a number line, and we've talked about the unit circle a little bit, but unit circle just means that you have a circle centered at the origin with a radius of 1. And then we've got this number line over here. All right, so, and I've got my number line drawn vertically just because of what we're going to do next with it, but you could draw it out horizontally. Make sure that, in fact, the distance from the origin to 1 there on your circle is the same as 1 unit over there on your number line. If that's not the case, then it's going to be tough to show this, but I can actually take this and drag this over here, and I should find that my starting point for my number line and my 1 on my number line up with that point on my unit circle there. So that looks good. All right, the next thing it says to do is place the 0 on your number line at the point 10 on the unit circle. All right, so I placed it at the origin, but let's move that here slightly. Take this and move it right here. So there's the point 10. I'll start my number line right there. All right, and then it says to wrap the number line around the unit circle in a counterclockwise direction. That's the direction we measure for a positive angle when it's in standard position, counterclockwise. Now, I can't actually wrap this thing around here, but instead I'll kind of simulate what it would do if I wrapped it around here. That if I started wrapping that number line around here, it would start to wrap around like this and so forth. It would go around in that direction. Maybe I won't draw an arrow there with it actually, just because I want to mark some key values here. But it would head around in that direction, a counterclockwise direction. And in fact, the 1 would kind of wrap around and land about right here, it looks like. And the 2 would wrap around and it would land somewhere about right here, it looks like. This would be the 1, this would be the 2. That'd be where that number line lands. And you can keep wrapping that all the way around that circle. Okay? If that were a piece of string, that would be kind of what we're trying to do. Wrap that piece of string around that circle. All right, I marked a couple of points, but let's talk about where the other points are going to fall here. So 1 should be in the first quadrant when you get done with wrapping that around there. You should find that 2 and 3 are in the second quadrant, so I marked 2. Let's go ahead and mark where 3 would be. 3 would be really close to the horizontal axis, not quite the horizontal axis. 3 would be about right here. It tells you that 4 is in the third quadrant, and 4 would be somewhere about right here. And then 5 and 6 would land in the fourth quadrant. So 5 would be somewhere about right here. And 6 is really close to my horizontal axis. I'm going to mark it right there. That's where 6 would be. And obviously you would continue wrapping around there. 7 would be back in the first quadrant, and so forth. I guess a couple of questions that you might have before we go on. If I'm wrapping this around this number line, or this piece of string around my unit circle here, where am I at when I hit the x-axis over here? Or where am I at when I come back around and hit the x-axis over here? Where are those points at? Well, if you're wrapping this piece of string here around this circle, then really what we're doing is we're working with the circumference of a circle. And I know circumference is 2 pi r. We're talking about a unit circle here, so the radius is 1. So that means that the circumference would actually just be equal to 2 pi. Which means that when I go all the way around one time, I should land at 2 pi. So 2 pi turns out to be one full rotation here then around this, which means halfway around must be half of 2 pi. This must be pi, which should make sense for us. Pi is 3.14, so I'm just a little bit past that value of 3. 2 pi is 6.28, so I'm just a little bit past that value of 6 that I marked in the fourth quadrant. So those seem to make sense. Pi and 2 pi. And if I wanted to look at the other axes, that's my horizontal axis. Where would it be here? Well, it's halfway between 0 and pi. That would be pi over 2. And what's this point right here? Well, that's halfway between pi and 2 pi. That would be 1.5 pi. I'm going to write that as 3 pi over 2 is how we usually write that. So those are actually some nice points to consider, but we have to write them in terms of pi. One thing to note there is that the terminal side of an angle with a radian measure of 1 will pass through the 1 that's marked on the unit circle. This is how we define what a radian measure is. So if I go back up to my sketch here, and if I look at where 1 is at, and if I draw a line that goes right through that point here, that'll be the terminal side of an angle that I've got marked here. And this angle that I've got here is 1 radian. I'll say 1 rad for radian. And of course, the line that goes through the 2 there would be at the terminal side of an angle with a radian measure of 2, and so forth. All right. So how do we extend this? If we're looking at the unit circle and thinking about how to wrap this number line around there, what if my circle had a little bit larger radius? How would that affect it? Well, by properties that we know from geometry when you're working with similar geometric objects, the arc and the radius are going to be proportional. The arc length and the radius that we're working with are going to be proportional to each other. So let's take a little bit bigger view of this thing. Let's suppose that I've got myself, I'm going to only look at a quarter circle here instead of the unit circle just so it fits on my slide here. But if I look at a quarter circle here and mark where 1 unit is on my x-axis, if I measure that distance of 1 unit here, it turns out that this arc length is going to have a measure of 1 unit, and that corresponds to a angle whose radian measure is also 1 unit. That's what we just saw there on the unit circle. So now what happens when we extend that? Well, the radian measure, the angle here, has to stay the same, of course. But notice what happens here when I double my radius. This distance here now is 2. And it turns out that if I walked along this arc length, I would travel 2 units. And that still is only 1 radian measure. That angle did not change at all. And of course, you can generalize this to any distance x that you walk along the x-axis there for the radius. And you walk along the actual circle itself there, you'll walk x units as well. But you'll still only have marked off a radian measure of 1 radian. The angle is still 1 radian. So what does that tell us about a radian measure? Well, here's our property here for a radian measure. A radian measure, then, is just the ratio of the arc length to the radius. If you measure your arc length and you divide it by your radius, that ratio tells you the radian measure that you're looking at. Which is why in the sketch that we have up above here, that when I look at my radius of 1 unit and my arc length of 1 unit, when I divide those two, I get 1. That corresponds to 1 radian for my measure of that angle. In blue there, we have an arc length of 2 units, a radius of 2 units. The ratio of those is still 1, which is why we have a radian measure of 1 unit. So this is how we actually define what a radian measure is. It's actually a ratio of 2 lengths, the arc length divided by the radius. All right. Big part of what we want to be able to do in this section is conversions, just understanding how we convert from radians to degrees and vice versa. So let's just take a step back and remember, how do we do any sort of unit conversion? You may have learned this in a number of different ways, but basically when you're converting units, really what you're doing is just multiplying by a clever form of 1. A clever form of 1 is a quotient whose numerator and denominator are the same, and thus it's equal to 1. So for example, if I just write this as x divided by x divided by x, of course, is equal to 1. So I'm going to multiply by something in that form, that quotient. But of course, the numerator is going to contain something that's in 1 unit. The denominator will be something that's in a different unit, but because those are equivalencies, the ratio is equal to 1. And it allows me to then convert from 1 unit to another. This is what we do every time we convert units, between units. For example, let's take something simple here. You probably don't even need to think about this one and to convert it. You just simply do the math and you know the answer right away. But if I want to convert 2.5 feet to inches, 2.5 feet to inches, how do we actually do that? Well, let's write out the calculation that we would actually do. You'd take your 2.5 feet, and we're going to include units here just so we can see what happens here with our units when we do this. If I want to convert to inches, that means I need to multiply this by a clever form of 1. And the clever form of 1 needs to get rid of feet and introduce inches. Well, 2.5 feet, I got to think of that as being 2.5 feet divided by 1 is maybe perhaps the way to write it, but I'm going to avoid writing it as a fraction there. But just realize the feet and the 2.5 are part of the numerator. So I need to multiply by something that has feet in the denominator, so that way the feet will cancel out. And I'm trying to convert this over to inches, so that means I want to have inches in the numerator. And now I just need an equivalency between the two. I know that 12 inches is equal to 1 foot. The number 12 divided by 1 is not a clever form of 1. But the ratio of 12 inches over 1 foot, that is a clever form of 1 because 12 inches and 1 foot are equal to each other. Notice that the units are important here. If you don't put units in here, then obviously you're not multiplying by a clever form of 1. But by including units, now I can actually cancel out the feet that will divide each other out. All you'll be left with is inches when we get done. So 2.5 times 12 sounds like 30 inches. Again, that's probably one that we don't even really think about. We just simply say, well, multiply by 12 and there's your answer. But what exactly is happening there? Why does it do that conversion? This is the reason why that works. This works regardless of what units you're talking about. Doesn't matter whether we're measuring lengths, if we're measuring area, or we're measuring angles. We still do the conversion the exact same way. The only thing that I need to know is an equivalency between the two units that you're working with, or a couple of conversions to help me get to the units you're looking for. So, what are the equivalencies that we have here? Well, from the sketch that we did there to define what a radian was, we marked a couple of key values there. And you could use, you could use anything you want here, to be honest with you. Probably the two that are natural to pick from are these two here. It turns out that if you go all the way around that circle with that number line, that 2 pi radians turns out to be the same as 360 degrees. That would be one you could use, but we usually just go halfway around. Pi radians was equal to 180 degrees. That was halfway around that circle. So pi radians equals 180 degrees. As soon as I know that, I can now convert between radians and degrees. Just like as soon as I know that there are 12 inches in 1 foot, I can now convert between feet and inches. Either way. So, if you want to convert from radians into degrees, we're going to say x is our radians and theta is our degrees. If I've got x radians and I want to convert it over to degrees, then I have to multiply by a clever form of 1. I would suggest to you that this guy right here is a clever form of 1 because 180 degrees and pi radians are equal to each other. And furthermore, you'll notice that the radians here will cancel each other out, and you'll be left with degrees. I can convert from x radians into theta degrees. Or I can go the other way. If I want to convert from degrees into radians, I would suggest to you that we've got ourselves a clever form of 1 right there because pi radians is equal to 180 degrees. This time you'll notice that the degrees is in the denominator so that the degrees will end up canceling each other out. And the units you'll be left with are in the numerator, the radians. So if I want to convert to radians from degrees, I just have to multiply by pi radians over 180 degrees. Again, the way you convert from one set of units to another is you always multiply by these clever forms of 1. All you have to know is that there are pi radians in 180 degrees. If you know that, you can do the conversion. I'd suggest that that's a better way to try to think about this problem than trying to memorize whether do I multiply by 180 over pi or pi over 180. That'll be a sure way to make a mistake every time. If instead you know that I multiply by clever forms of 1, include the units, things will cancel out for me. As long as I know that pi radians and 180 degrees are the same, I'm going to get the right answer. Let's take a look at a couple of examples here to do this conversion. So they want us to convert 135 degrees to radians. And 35 degrees. Again, the method you should be thinking about here is that I need to multiply this by a clever form of 1. The clever form of 1 needs to have degrees in the denominator, so it'll cancel out with the degrees in the numerator there. That's 180 degrees. And pi radians is the equivalent of that. So there's my clever form of 1. When I multiply these together, the degrees are going to cancel each other out. You'll be left with just radians. And so what are we left with? Well, when I multiply this, well, I'll have 135 pi divided by 180. This is in radians, which, by the way, we normally don't write the units of radians on here, but just so you can see that this is in radians when we get done, we'll write it there. And I would simplify this. I think we can simplify that quite a bit there if you find a common factor between the numerator and denominator. I think a common factor of 45 would work. So 3 times 45 is 135, and 4 times 45 is 4. So it would be 3/4 pi or 3 pi over 4. You could write it either way. Those are both correct. that, of course, is in radians. There's our conversion. Degrees to radians. Look at example 2. Example 2 now says convert 5.73 radians. That's not a very nice number, but that's what they want us to convert. So convert 5.73 radians into degrees. All right, 5.73 radians. So 5.73 radians, I've got to multiply this by a clever form of 1. My clever form of 1 that I'm going to multiply by has to have a radians in the denominator so that it will cancel out with the radians that they gave me. So I know that pi radians and 180 degrees are the same. There's my clever form of 1. My radians will cancel out. I'll be left with degrees as a result of this. And I would suggest that probably we want to grab our calculator and just see what we end up with this. If I take 5.73 and multiply it by pi over, or 180 over pi, grab your calculator and let's punch that in. All right, so with your calculator here, let's try this out. If we take 5.73 and we multiply by 180 divided by pi, and that's 328.304. In fact, I'll just grab a picture of that. Let's just jot that down. This is 328.305 degrees is our answer. And you should get more and more comfortable working with these different units and knowing where these different angles show up. Like, for example, if we go back to our unit, think of our unit circle there. Remember that 5 was somewhere around right here. 6 was somewhere around here. So I'm not sure exactly where 5.73 is, but we'll kind of mark it here. 5.73 must be somewhere around here. This is 5.73 radians. So if I'm trying to convert this to degrees, I should realize, well, if I'm converting this to degrees, this is 270 down here. And this is 360 right here. So I better be getting an answer between 270 and 360. Somewhere in quadrant 4, my answer better show up. And that's what we found, 328. That's where we ended up. If we go back to the previous example, let's talk about it as well. We should have done that when we were looking at it, but let's talk about that same thing. If I'm looking at the radian measure of 3 pi over 4, again, I should be getting more and more comfortable working with that type of angle when it's written in radians. So where exactly is 3 pi over 4? Well, again, if you sketch your unit circle here well, that wasn't a very good circle, but oh well. Here's 0. We said that this was pi over 2. This was pi. This is 3 pi over 2. So where does 3/4 pi show up? Well, pi over 2 is 1/2 pi. Pi is a full pi. So 3/4 of pi is going to be halfway in between there. This is my angle of 3/4 pi. Radians. Again, if you want to think about that in degrees to kind of help yourself see that, this again was 90 degrees here. This is 180 degrees. So 135 degrees, falls halfway between those. That's exactly what we found here. But again, we should get ourselves to a point where we don't need to convert this over to degrees in order to work with this angle that's measured in radians. Get more and more comfortable working with radians and know what quadrant these numbers are going to show up in. Whether it's written in terms of pi like you see this one, or whether it was a decimal number like you saw in the next example. That's the other part of what you should get out of this lesson here. Not only how to convert, but also what quadrant are these going to show up in when I go to sketch these. All right, that's the end of this first half here of section 6-4.